Welcome to this lesson on shunt voltage regulators. A voltage regulator must keep the load voltage nearly constant even when the unregulated input voltage or the load current changes. In a shunt regulator, the control device is connected in parallel with the load. It corrects the output by diverting or shunting a controlled part of the available current away from the load. We will first examine this feedback principle, then study a basic transistor circuit, solve a numerical example, and finally consider improved transistor and operational amplifier versions. The emphasis is on understanding how current redistribution produces voltage regulation. By the end of the lesson, you should be able to explain the operating principle of a shunt voltage regulator and identify the functions of its sampling, comparator, reference and control sections. You should also be able to describe how negative feedback responds when the output voltage rises or falls. For the basic transistor regulator, you will relate the regulated load voltage to the Zener voltage and the transistor base emitter voltage. You will calculate source, load and shunt currents in a worked example. Finally, you will distinguish the basic circuit from improved transistor and operational amplifier arrangements and recognize the principal efficiency limitation of shunt regulation. The unregulated input supplies current through the series resistor. At the output node, this current divides into load current and shunt current. The sampling circuit monitors the regulated output voltage and returns a feedback signal to the comparator. The comparator compares this feedback with a stable reference voltage and drives the control element. If the output tends to rise, the control element draws more shunt current. The larger current through the series resistor produces a larger voltage drop, bringing the output back down. If the output tends to fall, the control element draws less current, leaving more current available to the load. This is negative feedback because the corrective action opposes the original change. This slide follows one disturbance through the feedback loop. Suppose the output voltage rises. The sampled feedback voltage also rises, so the comparator increases the drive applied to the shunt control element. Shunt current therefore increases. Because source current equals shunt current plus load current, the increased shunt current increases the voltage drop across the series resistor. The output voltage is the input voltage minus this resistor drop, so the output is forced downward toward its set value. The opposite sequence occurs when the output falls, shunt current is reduced, the resistor drop becomes smaller, and the output recovers. Regulation is therefore achieved by continuous current redistribution. In the basic transistor shunt regulator, the transistor collector emitter path is connected across the output and therefore acts as the shunt element. The Zener diode fixes the approximate base voltage. With the emitter at ground, the regulated load voltage is approximately the Zener voltage plus the transistor base emitter voltage. The series resistor limits total current and develops the correcting voltage drop. If load resistance decreases, load current tends to rise and output voltage tends to fall. The reduced transistor base drive makes the transistor shunt less collector current, leaving more of the source current for the load. This action supports the output voltage despite the heavier load. Consider the given shunt regulator. The unregulated input is 22 volts. The series resistance is 120 ohms. The Zener voltage is 8.2 volts and the load resistance is 100 ohms. Assume a silicon transistor base emitter voltage of 0.7 volts. We shall determine the regulated load voltage, load current, source current and transistor collector current. Begin by identifying the current split at the output node. The current through the series resistor divides between the load and transistor branches. This node current relation provides the final collector current calculation after the regulated voltage and the other two currents have been found. First, calculate the regulated load voltage. It is the Zener voltage plus the base emitter voltage. 8.2 plus 0.7 giving 8.9 volts. The load current is then 8.9 volts divided by 100 ohms, which is 89 milliamperes. Next, the source current through the series resistor is the input to output voltage difference divided by 120 ohms. This gives approximately 109 milliamperes. Finally, apply Kirchhoff's current law at the output node. Collector current equals source current minus load current. So, it is 109 minus 89 or 20 milliamperes. The positive collector current confirms that the transistor has operating margin to provide shunt regulation. The improved shunt regulator uses two transistors. The additional transistor provides greater base current drive to the main shunt transistor, allowing the circuit to control a larger shunt current and therefore serve a larger load current. The Zener diode still establishes a stable reference. Resistor R senses the output related voltage and participates in setting the transistor operating condition. The regulated output is approximately the Zener voltage plus two base emitter junction voltages. Thus, the improvement increases current handling capability. Although the shunt principle remains unchanged, excess current is deliberately drawn through the control path to stabilize the load voltage. In the operational amplifier shunt regulator, the op-amp acts as a high gain voltage comparator. The Zener diode supplies a stable reference voltage to one input. A fraction of the output voltage obtained from the divider formed by R1 and R2 is applied to the other input. Any difference between the reference and feedback voltages changes the op-amp output and therefore the base drive of transistor Q1. The transistor then changes the shunt current. This changes current through the series resistor and its voltage drop until the feedback voltage again matches the reference condition. Higher loop gain improves regulation accuracy provided the transistor and resistor ratings remain within safe limits. A shunt regulator maintains output voltage by varying current through a parallel control element. The feedback loop always acts against an output disturbance. More shunt current corrects a rising output, while less shunt current corrects a falling output. In the basic transistor circuit, the Zener diode and base emitter junction establish the approximate regulated voltage. Current calculations must respect the node relation that source current divides into load current and shunt current. Adding a transistor increases drive capability, while an op-amp provides a more sensitive comparison between reference and feedback voltages. The main limitation is efficiency because current continues to flow in the shunt branch even when the load does not need it. This comparison places the two regulator topologies side by side. In the series regulator, the pass transistor lies in series with the load. The error amplifier changes transistor conduction so that the pass element develops exactly the voltage drop required to keep the output nearly constant. In the shunt regulator, the control device lies in parallel with the load. It maintains the output by diverting excess current through the shunt path. The table summarizes the consequence. Series regulation generally offers higher efficiency, lower normal power dissipation, and greater current capability. Shunt regulation is simpler, but it is normally reserved for low power loads, voltage references, or situations where the wasted current is acceptable. The position of the control element explains most of the practical differences. A series regulator places the control device in the load current path. Regulation is obtained by changing the voltage dropped across that device. So the same current that reaches the load passes through the series element. A shunt regulator places its control device across the output. The series resistor supplies both load current and shunt current, and the control device varies how much current it diverts. Consequently, a series regulator is usually more efficient and can support larger load currents. A shunt regulator is attractive when the circuit must be simple and the required load power is small. Remember the distinction: series control changes voltage drop, while shunt control redistributes current. Topology selection begins with the load requirement. Choose a series regulator when the load current is moderate or high, when efficiency and heat dissipation matter, or when good regulation is required over a wide operating range. Choose a shunt regulator when the power level is low, simplicity is valuable, or the circuit serves mainly as a voltage reference or clamp. A shunt design must still be checked carefully. At the worst combination of input voltage and load current, ensure that enough shunt current remains for regulation without exceeding the transistor, Zener, or resistor power ratings. For either topology, calculate the control device dissipation and provide an adequate thermal margin before selecting component ratings.